I can't see anyone now. All right. Who's excited about being at NDC? All right. Who had a good lunch? Who knows quantum computing? Who's heard the buzz about quantum computing and is kind of curious about what all of this is about? Well, hopefully this talk should dispel some rumor and probably make you ask a whole bunch of other questions. Because if you don't find yourself questioning your version of reality after you get an idea of what quantum computing is about, you haven't understood it yet. I think that's sort of a universal truism at this point. So my name is John Azariah. I work on the quantum team at Microsoft. We're building a quantum computer. This isn't going to be hugely a Microsoft-specific talk, but I will spend a little bit of time talking about one of the innovations that I've been directly involved in, and hopefully that will be of immense relevance to you as developers, right? So, of course, I mean, the first question we have to ask is why quantum computing? And the answer to that is actually a little bit of a homework problem. So this number is the product of two primes. Your homework assignment is to find out which two primes, right? If you could, a little earlier, a few years ago, that problem would have netted you $700,000 US. It's an intractable problem. It's actually quite a hard problem, and we'd like to keep it that way, actually, because as it turns out, being able to not being able to factor numbers is kind of the linchpin of security these days. All of our encryption is based on the fact that being able to factor a large number is classically hard. So hard, in fact, that it might take you a little while, right? And of course, we're going to find out why it takes a little while, and then we're going to see what we can do about that. Now, the bold claim that quantum makes is that this particular problem turns out to be specifically amenable to cracking in a quantum way. So it's not going to take very long at all once we get like some quantum hardware to play with. That's the bad news. The good news is that it's going to take us quite a while to get to the point where we can get enough hardware to do that. So before anyone goes off and feels that Microsoft is in the business of breaking encryption, I can assure you that to break a 2048-bit RSA number, you need about 4,000 qubits. The state of the art is that we have no qubits at the moment. So, right? Another interesting thing that I want you to walk away from is that 4,000 qubits is when you get it, 4,000 or 5,000 qubits, when you get it, will be usable for this kind of problem. But we can already protect against quantum. Post-quantum cryptography is actually a very real thing. And we already have a way to solve the fact that even though we can break factorization, we're not going to break encryption. And a third and more important thing is you'll find that you don't actually need 4,000 qubits to do something useful with quantum computing. We might actually find that there are very profound problems that we can solve, which will have a very profound impact on humanity with just a couple of hundred qubits or so. So well before you get down the point of destabilizing the world's economy, we might actually solve a problem or two. Now, let's actually go back and look at what makes this hard, right? So if you think about the number of bits and the time taken to factor, that's the 1024-bit line. If anyone can see the red line up there, that's the 1024-bit line. Oh, this is a 2048-bit line. In 2003, a cluster would take several billion years to solve that problem. Classically, in 2018 or so, we can bring that down to about 1 billion years. That's Moore's law working for you. And all you can see is that that curve is going to move slightly to the right. What we're talking about in terms of quantum computing, though, is a completely different computing paradigm, where we want to actually look at a line like that, like a 1 megahertz machine taking a few days, a few hours, and a 1 gigahertz machine taking about a minute and a half. So this isn't Moore's law amplified. This isn't a small incremental change. It isn't even business as usual. This is turning things upside down on its head to try and take advantage of specific physical phenomena that are happening at the moment in the quantum regime and making that useful for us. And that will have a kind of profound impact for certain types of problems. Now, the myth is that once we get the quantum computer, everything's going to be like completely different. And that is true for certain types of problems. It's not true for all problems. And that's the whole point of this talk is to sort of tell you what it's good at, tell you what it's not so great at, tell you where it applies, where it doesn't quite apply, what kind of programming model you're going to land up having. And that's kind of the introduction to the talk itself, right? All right. So up until a couple of weeks ago, this was the fastest supercomputer in the world. It's the Tiahe Lite. I believe that the US has actually built a faster supercomputer and taken away this title. But as of last year, that was definitely the fastest supercomputer in the world. And this is my favorite molecule. Kind of live on that. And it turns out that the supercomputer can actually model that molecule completely. It's a non-trivial problem because there's a bunch of atoms in there. Each of those atoms brings a bunch of electrons to the party. Each of the electrons interferes with other electrons in a way. The mathematics of this whole thing is relatively complex. It takes a fast supercomputer to kind of figure that out. But it can. On the right side, you're going to find a little molecule which is very, very important to the way in which we live, actually. And that molecule cannot actually be computed classically at all. Because it turns out that when you try to break down the problem just as you did for the caffeine molecule, you'll end up needing to be able to store something like 2 to the 200 and something complex numbers in order to calculate the full state of the molecule. And there's only 2 to the 150 atoms on this planet. So even if every atom on this planet turned into something that could store a complex number, and you had a computer that could access that kind of memory, this is still not going to be tractable for that. So classically speaking, this is an insoluble problem. And why it's insoluble, the impact of it being insoluble, is something that is going to be apparent in a couple of minutes. Now, I've kind of laid out to you that the whole idea that there is this kind of quantum behavior that's happening in a molecule that's representative of a very difficult math problem, right? And we are trying to solve the math problem, and we don't have a computer big enough. That's one way of looking at the problem. Another way of looking at the problem is to think that nature actually is using quantum computing already. It has the quantum computer inside. The atom's already doing the computation of the hard math. All we have to do is take a problem that we want to solve, massage it in a way that the atom can actually work on it, and use the quantum mechanical phenomena in the molecule to be able to solve the difficult problem for us. So that way, we take the natural phenomena that are actually representative of the hard problems and use it to our advantage. And that's actually what the quantum computer model is all about. We are effectively leveraging naturally occurring quantum phenomena, trying to understand them, trying to map our problems into that space, and let it do the work for us. And why is this important? Well, let's consider that molecule I showed you. Now, how many of you had a good lunch today? Did I ask you that question? I did, right? OK. Since 1911, all the food that we've been eating has come from industrialized farming. OK? And in 1911, two German gentlemen decided to find a way to make fertilizer. They make fertilizer using ammonia. And the process of making ammonia is the Bosch-Haber process. And it hasn't changed since 1911. And it's an extremely energy-intensive process to make this molecule. How much of it do we make? Well, we spend 3% of all the energy that we consume in the world making ammonia. It is the most important industrial chemical that we produce. And we use that to make fertilizer. So there's a huge energy cost associated with making fertilizer. But if you think back to how we fertilize fields before industrialized farming, one of the things that they did was plant beans. Now, it turns out that that's actually quite effective. What happens in the bean plant is that in the root of the bean plant, there are some parasitic nodules. And in the parasitic nodules, there are some bacteria. And the bacteria live in a cell membrane in an anaerobic space. And they use an enzyme called nitrogenase to be able to act as the chemical knife to break the nitrogen bonds and fix nitrogen from the atmosphere into the ground. This is being done at atmospheric pressure and at room temperature, which is not the case for the Bosch-Haber process, which you have to heat the ammonia up to a very high temperature and put it in very high pressure to get something going. The bean plants actually know how to do the fixing of ammonia. And that molecule that I showed you a few minutes ago is the core of nitrogenase. And what I just told you is that we can't actually figure out how it works. But if we could simulate that in a quantum mechanical way and figure out how this molecule actually worked by actually examining all of the electronic waveforms and the interactions associated with them and so on and so forth, we might actually be able to get a handle on how nitrogenase works and be able to make that an industrial process which cannot be done at this point. And you only need a couple of hundred qubits to make that happen. So a profound impact of having 200 or 250 qubits might actually be the ability for us to simulate nitrogenase and be able to actually take on the concept of figuring out how to do fertilizer better than we did 110 years ago, right? So that's $1 trillion problem. Chlorophyll is a similar kind of molecule. We can't figure out how it works. But if we could, and if we could make it work outside of the plants and we make it work in a way that we can actually industrially control it, we could handle carbon capture. In a similar vein, we can come up with more exotic materials like room temperature superconductors. And these are the kinds of applications that you're likely to see well before you get to the 4,000 qubit limit, where we start doing things like breaking, RSA, right? And these things only take hundreds of qubits. And the impact of each of these problems is actually quite profound on humanity. So this should give you an idea of the kind of applications that we're going to try and use quantum computing for. So to recap, the problems are going to be completely intractable to do classically. They involve modeling existing chemical processes using existing chemicals and the quantum phenomenon in them. And the impact of it is actually going to be quite profound, right? So with that, let me actually tell you how this whole thing works. So everybody here should understand the left side of this chart. Any problems with bits so far? No problem, right? 0 and 1. All right. Binary systems, bit vectors, we know how to make those dance. I mean, that's why we're here. We're at NDC, right? One of the cool things about any programming language that you have is that you can take an arbitrary integer, an arbitrary string, an arbitrary pattern of bits, and make a copy of that. Well, on the quantum side, you have a qubit, a quantum bit. It's also a two-level system. The two levels are actually two physical levels. But instead of representing them as just 0 and 1, we're going to represent them using a state vector. And how this is going to come up will be apparent in a couple of slides. I want you just to get the notation right, the terminology right. In order to do any operations on the state vector, we basically do linear algebra on it, right? And the fun part about it is that given an arbitrary state, a qubit being in an arbitrary state, or a set of qubits being in an arbitrary state, you can't clone that state just arbitrarily. You just cannot clone it to another location. And that's a physical limitation. That's the limitations of the physics. So there are already some similarities with classical computing, and there's some very profound differences. So I just want to lay them out for you, right? So if you look at the traditional bit, a transistor is either on or off, a light is either on or on, and you can actually use that information to store a bit in some location, right? And if you want to look at the state of n bits, well, if I give you a bit string of length n, that should be complete information that you need to get the state of n bits, right? The quantum thing's a slightly different kind of beast. So this is actually an interesting picture because it's a complete lie. It's actually a sphere in 4 space that's been first projected onto 3 space and then projected onto 2 so that you can see it up there, right? But really what it is if you imagine a single qubit being a beach ball and the North Pole and the South Pole being the two states, 0 and 1, then any point on the surface of the beach ball is a valid state of the qubit. So how many such points are there? An infinite number, right? So you can represent every single point on that sphere by just having 2 numbers, right? It's a polar coordinate system, so you can actually basically just store 2 numbers to represent every point on that sphere, and that's where the state vector comes from. So if you think about the qubit not being a single bit going on and off, but really a point on a sphere with a north and south pole, then every point on that sphere being a valid state can be represented using a single vector, right? And that should give you sort of a general idea of how this works. This diagram is called a block sphere. Unfortunately, you can't visualize 2 qubits. So you've got to take your mind up into like higher dimensions to be able to do this. But fundamentally, if you have n qubits, for every qubit that you add on, you have to double the number of state vectors, double the size of the state vector. And so if you have n qubits, you need a vector of size 2 to the n to be able to store the value. Okay? There's an infinite number of values, but you need 2 to the n individual coordinates in order to store the state of n qubits, right? And you run out of that very quickly, right? As I mentioned earlier, you have only 2 to the 150 or so atoms on this planet. There's only about 2 to the 250 or so atoms in the known universe that we can see, right? So breaking RSA is a little difficult classically. You can't actually represent the state vector because you need 2 to the 4,000 or something to be able to do that. And you don't have enough atoms in the known universe to be able to do that. So you run out of n very fast. So the trick with quantum computing is that the physical phenomenon, the atoms or the qubits, the physical phenomena that are exhibiting the quantum behavior, they're already capable of storing this enormous sized information. But nature won't let you look over your shoulder to figure out what the values are. So those are the kind of rules that you're playing with. So you can actually store this huge information with just 4,000 or so qubits, with the caveat that you can't actually get at all of the information when you want to look at it. So those are the kinds of rules in the quantum computing. So you guys must have heard about, oh, if you measure something, it collapses. That's where the whole thing comes from. So if you have this Bloch sphere, and your cubic state is somewhere on the surface of the sphere, you can't actually look at the sphere and say, where is the dot? Which point on the sphere am I at? The only thing you can do is ask the sphere, hey, where is the dot at? And it probabilistically tells you, oh, I'm at the North Pole or I'm at the South Pole. So you get one classical bit of information when you do the measurement. But while you do the state computation, you can actually store an enormous amount of information. And that leads to the kind of parallelism that gives us the speed-ups that happen in quantum mechanics, quantum computing. Now, no problems on the left side, right? Anyone not familiar with the NOT gate? Takes a 0 to a 1, 1 to a 0, right? We have the same kind of thing in the quantum world. It's called an X gate. It takes a 0 state to a 1 state and a 1 state to a 0 state. But then because the quantum state can be any combination of those things, the X gate has to do something smart. But before we go there, I want to show you how we can actually view both of those things in the same way. So let's assume that we are going to show the 0 state on the digital side as a vector. So let's say I have a vector representing 0 being 0 and 1. And the NOT operation is just multiplying by this matrix. And that takes a 0, 1 to a 1, 0. Right? No problem. I mean, it's very, very straightforward matrix mathematics. What it's doing is taking something that we're quite comfortable with and making it a little more difficult. But that's how maths works. Right? And the same matrix on the left side, when multiplied with a 1, takes it to a 0. So if you think about it, that matrix is effectively the NOT matrix. Right? And indeed, it is exactly that on the quantum side. So if you want to think about transformations of state on this huge state vector, it's always going to be a matrix multiply. And you usually land up with these huge matrices that effectively land up having to be computed and then applied onto the state vector to do the change of the state. A simple one for a two-qubit system is basically this little matrix. Just generalize this out to a very, very large space, and you've got quantum computing. That's really all there is to it. Right? Again, there are obviously many more matrices that you can actually come up with. On the classical side, you have the NOT gate and the NAND gate, and you have some general rules. In the quantum computing side as well, there are some rules. But again, if you think about n qubits, or if you just think about 1 qubit, you've just told me that there's an infinite number of points on the sphere. So obviously, with a finite number of operations, I can't get to an infinite number of points. Right? So I have to actually add the caveat that I can get to any point on the sphere given an epsilon, given a difference. I can then do that, and I can do that in a finite way. So the rules are slightly bent now. They're not quite as precise as the digital side, but they're close. Similar rules for De Morgan's laws and some mathematics involved there, which I'm not going to dive into. And then there's some interesting concepts like entanglement, which happen only on the quantum side. Now, entanglement is when you have a state of several qubits in such a way that you can't tell each individual qubit's state easily, or you cannot tell them apart at all. It's very unlike anything that you've seen in the classical world, because given a bit vector, you can always look at the nth bit and know what state that bit is in. in an entangled qubit state, you can't actually do that. So should give you some idea that fundamentally there's a lot of similarity that you can actually have from the digital computing side, but there's also a bit of weirdness involved. And that weirdness is really what gives us the benefits that we have. And it's actually quite straightforward, but involved to understand that weirdness. Have I confused everybody now? Is there anyone not confused? I'll try harder. Right. So what does a quantum computer look like? What does it mean to program the quantum computer, right? That's not a quantum computer. That's a fridge. Now, the quantum mechanics of qubit manipulation, like having a qubit and trying to get it into trying to behave like a quantum mechanical system, and being able to hold state for an arbitrary period of time or whatever it is a very fragile thing. It's a very fragile position to be in. So in order to actually be able to construct the quantum mechanical system that can have two levels that we can do computing on and so forth, typically we have to put them in a very isolated environment and chill the environment down so that it doesn't get affected as much as possible from the environment around it. So typically what happens is way up here, I don't know if you can see my mouse, way up there is where I typically sit at 300 Kelvin or so, 23 degrees centigrade, trifle chilly, wear a sweater. A little further down, you get liquid nitrogen, and this is about as cold as I've kind of played with back in the day when I was a chemist. Around 4 Kelvin is where liquid helium is, and also around the temperature of outer space. And we have to basically put some hardware at 4 Kelvin for us to be able to talk to the device. The device itself lives at 15 millikelvin, and it sits somewhere in the bottom of this thing, where it's completely isolated with several layers from getting even stray photon in there. Because a stray photon is sufficient to actually, in many cases, destabilize the qubit. So the engineering difficulties in getting a quantum computer out there are going to be phenomenal. And the upshot of this picture is that you're not likely to get one on your desk anytime soon, right? So the idea that we're going to have quantum computers and we're going to walk around with them in our pockets, well, that's still a little bit science fiction-y. Unless we actually get to the point where we can do room temperature superconducting and so on and so forth, it's going to be very difficult to get this outside of a data center, actually. So the engineering involvement here is for us to be able to create classical control for controlling the qubits, actually get the qubit itself in place, put the whole thing in this isolated environment, stick the isolated environment somewhere, and then be able to access that over the internet. So if you really think about the logical computation model of it, it's going to basically be an adjunct external coprocessor. That's really what it is. So you're always going to have a host program that you're going to run. It's going to do all of your I/O and all of that stuff. You're going to read from files, interact with the user, whatever it is that you need to do. And what you'll end up doing on the quantum side is effectively the difficult math that you can't do locally. That's exactly the model of a coprocessor, except that the coprocessor doesn't sit inside your machine. It sits externally. So if you think about the logical model, you're never going to work with just the quantum computer. You'll never actually directly work against that. You'll always be interacting with it through some kind of a host program, which ships off the work that needs to get done on the quantum side and then gets the result back. So this is a very sort of subtle but profound sort of realization, because what it means is the way in which we interact with this thing has to actually be thought of in that way. There's asynchrony involved. There's actually two different computation spaces. And so people who do things like graphics programming, they already have this mindset in their minds about how to actually do difficult work on the quantum side. Now, if you went off to Microsoft.com/quantum and downloaded the QDK, you will get this stuff in the light blue already for you. It's already there. And when you run a piece of code now, you can write the code in Q#. You can include libraries that have been written in Q#. You write your host program in whatever language you want. It's C#, Python, F#, whatever you feel like. And then you run the thing against a simulator, which does the math for you. Now, obviously, the math is being simulated on your local classical hardware. So there's limitations on how big your state vector can be. A reasonable laptop will give you 20 to 25, maybe 30 qubits if it's got a large enough set of RAM. If you feel flush, you can go up to Azure and run the thing on a simulator cluster over there, and you can get up to about 40 qubits. So it's still not to the point where we're able to do anything earth-shatteringly difficult with 40 qubits, because you can do everything that you can do on the quantum side classically, right? But it gives you the ability to actually start developing quantum algorithms and being able to characterize those algorithms. And part of what I do is get the software layer up. So there are many layers, as I showed you. We have the hardware. We have the quantum hardware that does the quantum computation. We have the piece that actually does the control of the qubits, and that runs at 4 Kelvin, so that's actually quite cold, and there's a lot of engineering challenge involved there. And then you have, obviously, the stuff at 300 Kelvin, which is really the quantum libraries and the quantum language that we've built. Someday you'll get the quantum hardware, and that will actually do the real computation. But you can take the same program that you have and just run it directly against the quantum hardware when it becomes available. And so the logical computation model is well underway. We already have a good start for people to start playing with this thing. What does a quantum program look like? Well, on the left side is what is known as a circuit. And if you're familiar with electronic engineering or electrical engineering, there's a similarity in there. What I've shown you up there is actually 3 qubits called message here and there, a classical value that's either true or false, and time sweeps from the left to the right. So if you think about it, you've got qubits going from top to bottom, and every time you want to add an extra computation, you have to add an extra line. And then they have these various operations. The X gate you've already met. There's another gate called the H gate. Then there's that funky-looking symbol, which is a 2-qubit C0, and so on and so forth. There are a bunch of gates like this. And if you go and look at the literature, you'll find that most quantum algorithms are actually described in terms of circuits. And this is a problem, because if you want to add 2 numbers, you have to start by saying how big those 2 numbers are if you want to construct a circuit for them. You can't simply say, here's 2 n-bit numbers, let's draw the circuit, without specifying what n is. And so unless you want to draw out a circuit for all possible values of n, you need to find a way to generally describe what the computation sequence is going to look like. And for that purpose, we came up with a new language. Now, I'm going to explain to you why we had to come up with a new language in a couple of minutes. But the language is actually on the right. And it's actually a faithful representation of the entire circuit on the left. In fact, the variable names are exactly the same. And as it turns out, the language will allow you to express general circuits without having to specify the size, for example. So in some sense, the language is already representing a strictly greater set of things than the circuits will. And this comes in very handy, because now you can ship a circuit as a library, as a parameterizable library that somebody can use. So the question is, why do we come up with a language? Why didn't anyone else come up with a language? And the answer is actually in this grid. So there are other people, our competitors and collaborators, who've come up with qubits and ways to interact with them. So you can go up to IBM, and they have a 5-qubit and I believe, a 49-qubit or something device in the cloud that you can actually interact with. You can send a program, and it'll batch up and run on the hardware. But they don't use a different language. They just use Python with a set of libraries. And it turns out that that approach is effectively this column over here. And it's actually sufficient if all you want to do is simulate and retarget, which is really the exact use case that they have right now. So if you want to run it against a simulator and then take the same program and run it against a real device, you can do that with just a plain, straightforward host language and a library. What we've figured out, though, is that if you want to ship a set of library functions that already have quantum algorithms built in, then that model just does not work, because it's effectively impossible to write this in terms of standard classical library functions. You can't compose those easily. And so in order to be able to ship out a library, you have to express the quantum computation in a way that allows it to be composable. Similarly, there are certain optimizations now that we can do if we can actually look at the program that you're trying to write and say, hey, I know how to actually reduce this computation that you're trying to do by applying the mathematical laws of linear algebra. And in order for us to be able to do that, we have to comprehend the intent of what the programmer was trying to write, which is virtually impossible to do if your library calls are actually just mangling some state vector somewhere. You won't be able to understand what they're trying to do, because what you really want to be able to do is read the program that you've written and try to understand that. So the ability for us to be able to reason about the behavior of the thing leads us to be able to represent the program in a way that we can reason easily. So we have to come up with a way of doing that. The other thing, of course, is that if we originally started by writing everything in F#, and we found that F# is both too permissive and too restricted. It's too permissive because you can do a whole bunch of stuff that the F# compiler will not complain about, and which were perfectly valid F#, but which have no meaning whatsoever in the quantum space. So you can write completely nonsensical programs from the quantum side of the world in a program that the compiler cannot help you to say, hey, you're doing something stupid. So the ability for us to be able to do that means that you have to limit what the language does to the set of things that make sense in the quantum world. Similarly, and actually conversely, you can't express certain things that you want to express from a quantum side in a traditional language. The example for that is actually this. The quantum programs are all probabilistic. So usually you never just run the program, get a result, and you're done. You never do that. Because every time you just ask the Bloch sphere, hey, which point on the surface is this? It tells you that it's the North Pole or the South Pole probabilistically. And so you may get the wrong answer. So what you'll end up doing is sampling. You have to run the program a bunch of times and then sample or do machine learning on the result to be able to figure out whether the result that you got is actually the result that you wanted. And so to be able to express that kind of iterative construct, you'll end up having to do some really crazy things in a traditional language to be able to express that. Whereas that kind of construct is native in a new language. So basically, to handle all of these specific reasons, we've actually come up with a new language. I'll give you an example. One way, so qubits are pretty precious, right? I mean, even if you Google, you've got like 72 qubits. They're kind of noisy, but they're there. And what you'll end up doing is you only have 72 qubits. So if you want to do something, you're limited by the number of qubits you can play with. But it turns out that you can actually have algorithms that reuse a qubit that's in computation at the moment, as long as you don't change its state to something else, right? So you could be able to borrow a qubit to do something and then return it in its original state. Well, that's extremely difficult to do if you have to do it across all programs. But a compiler can do that for you. A compiler will know what qubits are in scope and what qubits aren't, so they're able to do this kind of optimization. And you can also estimate how long a program is going to take by just running the program against a simulator that doesn't do anything except count the number of operations that you're doing. And this turns out to be very useful because the same molecule that I showed you earlier, we were able to figure out how to improve the algorithm to run in a very, very fast time by just using the characterization simulator. So just the ability for us to do all of these kinds of things sort of steers us in the direction of having a different language altogether. I'm going to skip over this symbolic computation stuff because some of it is a bit involved with algebra and stuff. But basically, the language features are its familiar block style, as you can tell, but it's heavily inspired by functional programming, as in you have concepts like immutability by default, first-class functions, partial application, and all those kinds of things. And then we have, obviously, the quantum-specific concepts that I alluded to earlier. So I think what I'm going to do at this point is stop blathering on about and show you some code. Now, before I get into the code, let me explain what teleportation is. Remember how I told you can't take an arbitrary state from one qubit to another? Well, how do you actually do anything then? What you'll end up doing is you have this circuit that you can use that will take the state of one qubit into another qubit whilst destroying the state, right? And that turns out to be very useful because teleportation is effectively the only way you can actually move things around. You can move arbitrary states around. And so this is effectively the hello world of quantum programming. And what I've got here is Visual Studio, and what I've got here is Q#, and I've set a breakpoint on my Q#. And I told you earlier that there was going to be a host program, and indeed this is the host program. It's written in C#, and I'm going to teleport first true and then false. So remember that circuit that I showed you earlier, which had a Boolean value up front? Well, I'm going to send both values, one after the other, right? And I can now run this thing. That's interesting. That's very interesting. But if you notice here, I sent in true, and I can now observe true. Can I observe what the state vector is? The answer is no. Because if the state vector, where is the state vector actually being stored in the quantum device? It's being stored at 15 millikelvin on some exotic computation device, right? That will collapse the moment I look at it. So I can't go in and probe the thing to look at what the state vector is over there, but I can look at all my classical values over here. So the simulator here is quite faithful in that regard. It will protect you from doing silly things. Now, flag is true, so I'm going to step in. Let's see what F10 does. And indeed, I'm about to run X on that. And I can go off and run this, and I get that result, which says that true is teleported successfully. And flag is now false over here. So I can run it again. And I've teleported true and false successfully. So the tooling and the development environment that we have is very important. I mean, if we want to actually introduce people to quantum programming, we have to give them not just the device or the simulator, but also a language now to write the code in, and tools associated with it to help you do debugging and so on and so forth. And then we can go off and actually look at the code in more detail if we want. So for example, I can refactor that code out and use some of the strong typeness of Q#, which doesn't interfere with the type system of the host language. So the kind of separation that you get out of it, you get some very sophisticated benefits out of that. And I can show you Q-sharp in far more detail tomorrow. And there are 2 deep dive workshops that are back-to-back. So if you're really keen on looking at what Q-sharp is and how it actually works, come to the talk tomorrow. And I will actually not bore too many people with the details at the moment on this one. So one of the other benefits of having a language is that you don't have to write everything yourself. There's an open source project with the entire quantum library that's basically contributed to not just by the people on the team who are all quantum physicists, but also by people in the community. And you can take and use all of these functions and the building blocks, and the compiler will make sure that it does the right thing. So just having the ability to have a new language allows us to expose a fairly sophisticated set of libraries and extensive documentation that you can basically use to run with it. Right? Again, I'll be diving into this a lot more detail tomorrow. So you can go in and try it out now if you like. Just go to microsoft.com/quantum. It will give you the quantum development kit, and you can get started as quickly as you like. I'm going to call it at the moment. It's 51 minutes into the talk. And I will take questions, because historically I've found that there's a lot of questions that people want to ask. So that's it from me for the moment. But yeah, thank you. So I'll take questions. Anyone at all? Yes.
How far away from the first qubit computer?
Okay, so the question is, how far away are we from the first qubit? Okay, now I have to put on my Microsoft hat, right? So our goal is to get the first qubit out by the end of this calendar year. That's what we've announced. That's what we're working towards. We're hoping to get a fully functional machine. I think the announcement was that we were going to get a fully functional machine within the next 5 years. So the race is on to actually get a topologically protected qubit. We're working very hard at that. And we're making significant amounts of progress. But we haven't announced a qubit yet. Any other questions? Yes, sir. Yeah.
You said that there are performance improvements when using the quantum logic for solving certain problems. Would using that logic with the simulator also provide performance?
Okay, so that's a brilliant question. The question was, if you use quantum algorithms, you get speed up for certain, certain problems. Can we get the same algorithmic benefit by using the simulator? The answer is yes, but the simulator is actually very small. And that's one side to the answer. The second side to the answer is that there's an entire universe of quantum-inspired optimization for classical algorithms. That is a reality. So there are many algorithms that are difficult right now in a classical sense. But if you take the quantum approach to doing certain things, that lends itself to actually allowing you to optimize a classical algorithm in a non-traditional way that gives you an enormous amount of speed up. So there are several problems that we've actually solved using quantum-inspired optimization. So that's another real benefit that comes out of studying the quantum computer science right now. Does that answer your question? You, sir.
You said you have to sample actually to figure out the state in the end, right?
Yes.
Is there some kind of confidence factor whether the result is actually correct or not?
Okay, so the question is, because you're doing statistical sampling to get the result of a quantum computation, how confident are you that the correct answer is actually produced? That's actually the thing that we're sampling for. Because when you sample, you'll get a result. But when you sample many times, you'll get a result with a probability that says, hey, probably this is the right answer. And that's really what you're shooting for. So it's probabilistic computing, but with a significant caveat that there's a lot more going on here.
But there's still the chance that it's not right in the end.
There's still the chance that you get the wrong answer, yes. Which is why quantum algorithms tend to take quite a long time to run and a long time to verify correctness. Yes. Yes, sir.
Do you think we will ever need a quantum computer with more than 640k bits?
Are you trying to put me on the spot or something? The question was, are we ever going to need a quantum computer that has more than 640 what?
Qubits.
640,000 qubits. Historically, somebody said something like that once. I'm not sure I want to go down that road again. Yeah. Anyone else? Yes, sir.
Another question. Do you run into problems with doing a calculation? Because with classical computers, you can store an in-between result, while with quantum mechanics, storing in-between result means measurements mean destroying the state.
I've kind of lost the thread of your question. Maybe after? Sure. Yes. Anyone else?
Yeah.
Cool.
Do you also work with string theory and any of that sort of?
Do I work with string theory? I do not know quantum mechanics. I'm not a quantum physicist. I work with a bunch of really, really smart quantum physicists. I'm a mere software engineer. So no.
But is it a part of the research team, or is it a part of the research at all?
There's a whole bunch of research that I don't understand. So quite possibly the answer is I do not know. And that is actually the correct answer. A vague quantum answer too. It could be. I don't know. Yes, sir. Last question.
When I was studying quantum computation many years ago, and at that time there were only very few algorithms where you could actually get a significant speed up over classical.
Sure.
So you had the factorization and the search algorithm.
Sure.
So how is this looking today?
That's a brilliant question. So what are the building blocks of quantum computing that actually give you a speed up over classical, right? And it turns out that there's actually only a handful of algorithms, handful of building blocks that effectively form the foundation for any quantum attack for a problem. That number is still very small indeed. I think you mentioned most of them already. So there's factorization, which is a result of basically doing wave interference, and then there's a kind of search that you can do that happens in log n time or square root n time. So you get basically only a few building blocks in terms of new algorithms that take advantage of this stuff to get you a quantum speed up. And there's trotterization, of course, which is decomposition of the Hamiltonian. But other than that, there's not all that, not too many more that I know of. But you shouldn't take my answer for this. You should actually contact, for those people who are going to view this on the video, they're far more qualified people than me who can explain the quantum mechanics of it. Yes, I think that's it. Thank you so much. Thank you for coming. Cheers.